topic, but we'll stretch it over. The simple way of thinking about sequences is just functions, but our practical purpose is much broader. And I just want, instead of trying to tell you about it, I'll just go on and show what we have seen and what we can do with it. So this is number one, is what we did previously, not a long time ago. So this was what we did. If you remember, we plotted the circle. Okay, so what's happening here is, so first of all, you can tell that these are a bunch of separate points, and what is how we made them, or how do you create a circle from this? And the answer is by our formula. Remember, 1 square root of 1 minus x squared. But also, what actually interests us here the most is the relation between the rows and these x's. So let's just concentrate on the first two columns here, like this. So it doesn't really matter what our formula is. The point is the correspondence between these. Let me put n here just to make that point clear. So these are the integers. These are the inputs of our sequence. So for each n in this column, we have an x in that column. Okay, so that is the correspondence. So you can think of it as simply a function. Every function can be written in that way. One column is for the inputs, the other one for outputs, and how you get from one to the other is secondary. There are just so many ways you can do it, and this is just one out of 100. Furthermore, the functions that you have seen previously have been visualized in that manner, but on the other hand, we thought of x's as real numbers. Okay, so hypothetically, every number between, say, 0 and 1 can be the input of a function y equal x squared. Very good, but there is no way you can have infinitely many numbers plotted. Okay, so every picture you see in the book or in computer-wise that looks like a curve, it is made of just maybe 100 or 1,000 points. And how do they make them? That's how we make those points. So all of those are sequences, and they put points close enough to each other, and they create an appearance of a curve. So we just make it more and more explicit here, and that's you can see. So you can even see what's happening as we are progressing to the right over there. They are getting so close to each other, they are almost overlapping. They're also an option in Excel that can even better fool you into thinking that that it is a curve, even though it's made of points. So there is a chart type. Okay, scatter plot. Oh, here it is. So see the options. You can have separate points to begin with. Okay, so that's number one. See. The same points, there is no connection. So originally it was points and connections, now points with no connection, and you can imagine what if we plot nothing but connections. Then, well, what is going to happen? Well, it will simply look like a curve. So it's all a ruse. It's all an illusion. So the data that Excel receives is on the left. All of those numbers, pairs of numbers. It plots those numbers and then connects them by a curve, and then hides the points. If it hides the point, as I just did, then the total appearance is that the illusion is that it is a curve. Okay, so that's the importance of sequences in comparison to those functions that seem to be very natural. And if you're thinking about, say, motion, you like to think about motion as a continuous process. So if you get from this point to that point, you have visited every single point in between. So you did not hop several times from one point to the next until you reach the destination. You think of it as a continuous process, especially time. Certainly, there are no gaps there. So, but that's all fantasy in the sense that we are just like to think that way. But if we're doing any kind of computations, then yeah, that's the only way. The only way is to compute that computers cannot do anything else. So they don't do continuous. They have to do discrete. They have to do incremental, and that's why what you see. In fact, Excel connects those dots that we just saw, connects them into think about this, connect them into curve this way, right? And connect to a curve, but that curve is also made of dots. Okay, so it's all an illusion again. So just one illusion that was explicit. Well, so explicit that it was not an illusion anymore, this one. And then they just made the same illusion on the batter. So this is, say, I think 40 points, and it looks like separate points. Now here maybe 1,000 points or so, and then it looks like a curve. So if it is a computer, there is nothing continuous. It's all made of dots. You might even remember that the screen is made of little pixels, and whether they turn on or turn off, that's what it makes all the difference. And so you increase the resolution, and the illusion becomes better and better. But still, behind it, it's always the same story. Okay, so that's the why we want to have sequences in the first place. Anything related to computers, modeling, simulation, all ultimately requires sequences. Okay, so this particular one, the curve we're looking at has two sequences simultaneously plotted. So as you can see, because there is an x and y, but I could plot certainly separately x as a function of n. Okay, so I am ignoring y, and I'm plotting simply how x depends on y, and just to make that point, I'll plot it with bars. Oops, that's not the right bars. Maybe this one. There it is. That's right. Okay, so that was highlighted on the left. I plotted on the right, so you can see it as the way you just started from the very beginning. The x-axis is where n's are located. Okay, the horizontal axis, and they run between 1 and 12. Okay, well, it should be 11. It's from 0 to 11. Okay, and then the heights of those bars are the outputs. And then I can do the same with y, and that's what makes up a curve. Okay, so all right, so that's the main idea. That's how we do sequences. One thing, however, this is not the most common way of producing sequences. Once again, look at, well, let me do y's instead. Now let me start over. Yeah, let me start over. Okay, so I'll make up a picture of a sequence. So I'll be putting n's here, starting with 1. Okay, and I'll put a. Let's maybe put it this way, a n. Okay, so remember the notation for sequences is the letter that is, say, a, the name of your sequence, and then a subscript n indicates the place of that particular entry in the sequence. So so this one will be the first, and say let's pick a simple sequence 1 over n. So it's equal to what is it? 1 divided by this number. Okay, so RC minus 1 means same row, column, previous column. Okay, enter, so we have 1. And then I can have a few of them. Okay. I'm sorry, I forgot to do what I was supposed to do. I need to progress with n one at a time. So this one is equal to the previous one plus 1. Okay, so that way I have all of them available. Okay, so you can see what is happening here. Okay, so once again, only the data is visible, but the formula is still there. So whichever I pick here, that is the formula in C1 divided by RC minus 1. Okay, from the previous column, you can see that the green entry depends on the blue entry in the previous column. Okay, so and that creates my sequence, the sequence that I can now plot like this. So I highlight and I do a chart. Let's see, a good chart. What is this? Waterfall. Okay, this would be okay. No, it's not. There's just too many varieties. Far from perfect. Yeah, let me try this one again. I don't know what this is. Okay. I guess I'll have to go with this one. Scatter plot again. Yeah. Okay. So so you can see on the horizontal axis you can see ands. Running from 1 to 18, and then in the values on the y-axis we put our second column, these numbers. Okay, so and you can see how we're progressing from left to right. And once again, if we had more points and they're close to each other, it will look like a curve. Okay, and then we see something familiar from calculus 1. What is that? What kind of behavior? What do we call this behavior when it behaves like this? It is a horizontal asymptote. Indeed, then the function 1 over x has a horizontal asymptote y equals 0. Okay, so and they're approaching then this value. So, but other than that, you can discover that unlike graphs, unlike functions, you usually need graph. Here you could discover the same thing by means of simply direct examination. You can see you can examine these numbers and notice the pattern. You can see where these numbers are going. You start with 1, and then all of a sudden you have 0.6, 0.06, 0.06, so it's getting smaller and smaller and smaller. And based on that analysis, you might say, well, then it is definitely going towards 0, and that will be your idea of limit. So remember, asymptote is a description of what you see on the picture usually, but on the graph, a certain pattern of the graph of flattening of the graph as you sort of almost merge with a particular straight line. That's horizontal asymptote, but ultimately it is described by using limits. So that is a limit of our function 1 over x at infinity is 0. That's from calculus 1, and now we actually doing something simpler. We're saying that the limit of 1 over x, limit 1 over n goes to infinity, is 0. So compare this. So this is new, and this is old. Limit 1 over x goes to infinity, is equal to 0. So what is the difference? Really, the difference is negligible, and what you can actually see the difference here. Imagine that this turns into a graph the way I did previously. You can see the function and the sequence in the same picture if I just once again add the curve like this. Okay. Okay, so you can see the dots is my sequence. Well, let me maybe tweak it a bit. How about? Okay. So the sequence is the blue dots, and the graph of the function 1 over x is red. Okay, they are both together. So in a way, we take our graph and sample it several times, so that as many times as necessary. But it still follows it. It still follows it, and so the function, in a way, that function defined everywhere, has more information, whatever is happening in between those gaps. So it's more complex. We are moving from something to something that is simpler. Okay, sequences are simpler, and that is an example. So let me tweak this a little bit to see the different behaviors. For example, the limit was clearly 0 over here based on the picture or the analysis of numbers here. I could say add 2 over here. What if I take my function and simply add 2? You can see what the whole thing looks like that. So it's the same behavior roughly, but as you can see, the whole graph jumped up by 2. So whatever you saw in calculus, what happens to functions, if you say add f of x plus 2, what does it do? The graph goes up by 2. Same thing happens with sequences. Okay, so how about so the sequences might oscillate. Let me try. The sequences certainly can oscillate. I just need to pick. Okay. So how? Let me copy this. Come on. What? Okay, let me enter something else. So if I want a function that is not only has an asymptote, as if you wish, if you like, but also goes up and down. So I don't want this confusion that happens sometimes in Calculus 1 when the assumption is that the asymptote has to be approached from one direction. So it's either from above or straight from below. You can actually oscillate and approach a certain function gradually. So I just enter what functions do you know that oscillate? Drake function. So how about I go with sine of, well, let's try sine. It's actually quite a picture. Sine. So this is sine of n. Sine of n. Not sine of x, but sine of n. Let's see what happens. Or maybe can you predict what's going to happen? Sine evaluated at 1, 2, 3, 4, 5. What kind of pattern do you expect? Well, not something that is foreseeable. Well, it is actually quite foreseeable. So it goes up and down, but still in a fairly predictable manner. So the sine function is roughly still there. But once again, the red curve is added by Excel. In fact, I don't like this. It's just too. I want to make a point clear. Recognizable. Writing texture, picture, color. I just want to make it bigger. How do I make it bigger? Too many options. Well, anyway, so the red dots are our sequence, and the green curve is whatever Excel adds to it. So this is definitely not sine because sine is way looks more smoother, and well, Excel doesn't know that we're plotting sine, and so it just try to add a curve from a point to the next. Okay, so that's best we can tell. So it oscillates. How do I make it? How do I shrink it in such a way that it would converge towards the x-axis? So remember this, the sine function gives me this oscillation. On the other hand, 1 over x, what we just looked at, was here. sine 1 over x.
Would be every period of the function.
What?
Every period of the function would be its sequence.
Okay. Well, the period is 2 pi, and what we're seeing here is, see, because we are not following the period, which is 2 pi, but rather we are following simply the integers. That's why the heights of those red dots are actually quite random. They don't really follow. It is, as you can see, these are not exactly at the very top. It is actually surprising why they're kind of close to each other. Yeah, but it is pure accident. Well, what I'm talking about is I want to shrink this and have a limit for the sequence, and shrink it not simultaneously but rather gradually, so it will be thinning out. One way to do it is to divide by higher and higher numbers. Okay, so then it starts the same way, and then gradually will go down, will be shrinking. So divide by 2, by 3, by 4, by 5, and it will be starting to thin out towards the x-axis. So that's what I'm going to say. I will simply divide by once again by n. I'm dividing by n. Okay, like this. Okay, you see what's happening? So here, yeah?
I got a question.
Yeah.
Alright, so if it was like the limit as x approaches infinity of 1 over n plus 2, would that make it equal to 2 since it shifts it 2?
No, the limit would be 2, yes. Yes, yeah, you add 2, which means that you shift the graph up, and simultaneously you shift the limit up as well. You shift the horizontal asymptote up, and you shift the limit up. So it's like literally a picture drawn on a piece of paper, and you shift the whole piece of paper up. So nothing really changes. So it's just rescaled.
Is the x plus 2 like together under the 1, or is it plus 2 outside?
Well, that is presumably this plus 2. Let's take a careful look at what I just did here. You can see where that is. I can understand that it might be ambiguous because of the notation, right? But this 2 is outside. So we first divide, and then we add 2. Let's do the other one. How about to have 2 in the denominator? I will add parentheses like this. Okay, you see the difference, right? So now I divide 1 by the whole thing here. What do you think is going to happen to the graph? It will the original one, the original of 1 over x, 1 over n graph will be shifted indeed, but this shift will disappear. As far as this graph is concerned, it will go all the way down, and well, this is what's happening. So it's almost identical graph to 1 over n. Okay, so almost identical, except instead of starting at 1, we're starting at 0.3. That's the only difference. Okay. Okay, so this one is simpler. Well, there is no shift, but you can see how accumulation starts. How accumulation starts, let me write out, if it is, the formula is right here, but maybe if I just write it out for you, it will be slightly more readable. So what I'm talking about, the sequence is 1 over n, well, let's just say, so the fraction is sine n, which gives you the oscillation, and then I divide by n. Okay, so sine n lies between -1 and 1, right? In the meantime, n goes towards infinity. So sine n between -1 and 1, as we know about trig functions, and then it means that sine n over n lies between -1 over n and 1 over n. Does this kind of inequality look familiar from Calculus 1? I wonder. What's the limit of 1 over n? 0. Limit of -1 over n? Also 0. So, which proves that the limit of sine n over 1 over n is also 0. According to a certain theorem, if you remember the name, is squeeze theorem, yes. So it is a squeeze theorem, which we had for functions, and now we have them for sequences too. Okay, so like I said, a lot of things will reappear in the exact same way for sequences as you saw them in calculus 1 for functions. Okay, and that you can see the conclusion according to the theorem that that I worked out here. You can see it here. Okay, you can see how oscillation continues. At no point this oscillation of going below above the x-axis will disappear. It will continue on, but the swing of the oscillation will get small and small and small, and it will, as you can see, will eventually virtually merge with the x-axis if we give it more time, which is really more space rather. Let me do that. If this is not quite impressive, let's take it a little bit further. So as you can see where the values, you can see what's happening after 190 iterations, what's happening to the values. They're almost zeros, as you can see, 2 digits, and then almost nothing is left. So let me expand it. Well, you can imagine what's happening furthermore. Jump. Okay. Yeah, see, I stretch the graph all the way to the right, 190 terms, and as you can see, oscillation does not disappear. It oscillates at the same frequency as before, but the swing of the oscillation, the amplitude, if you like, diminishes up until nothing, and as you can see, indeed, it will become flat. Ultimately, it will become flat, so much so that you won't be able to tell it apart from the x-axis. Okay, so there are more sequences, but what I want to do instead is look at a different way of representing sequences, and that is the idea is recursive. Anybody familiar with the idea of recursion? So what is it?
When you're kind of, well, I'm familiar with it, like programming, right?
Yeah, it is. That's where it comes from.
Yeah, so when you run a recursive method, you are running the method within itself to solve the problem.
Right. So you right. So you have one method, in other words, maybe a formula, and you reapply it again and again and again, producing more and more numbers. That's what's going to happen. So compare what we have here, exactly opposite of, not opposite, but very different from that. We have an explicit formula. We have an explicit formula for an. So this is an in this column. This is n. So, and as I said, an depends on n. And this is the formula you can see here, simply 1 over n. 1 over n plus 2, period. Okay? And the formula is explicit. However, it is very, very common to produce a sequence when there is no explicit formula. There is only a formula for producing the next entry in the sequence. So you go like this, one at a time, without referring to n. So, for example, I could start with, say, 1, and then, give me a formula that any formula. I don't know, equal to, so I look at my reference. I will be referring to the previous element. I will not be referring to this element where the value of n, the entry. It's like the way always has been with functions. I will be referring to this one, the previous element of the sequence. So it will be, let's say, this element. How about 1, interesting, 1 divided by the previous entry plus 2. I don't know what's going to happen here. Okay, let's see what's happening. So as you can see, it converges pretty quickly. A bit surprising, I'd say. So as you can see, the formula, once again, I am computing, I am taking, how did I get 0.33? I took this 1 over here, and I divide 1 plus, 1 divided by 1 plus 2, which gives me 1/3. The next element, I take the same formula and apply it to 0.33. So it was 1 divided by 2 plus 0.33, and that's how I got 0.43. Okay? So as you can see, the rest of the what the output of this procedure is still the same. So you have a column of n's, but now there is no reference. Just to make my point here, let me show you. If I, okay, that's not working. A point I was trying to make is that the values of n do not participate in this process. Let me. No, I don't think I can get around that. So, but only the previous element of the entry. One especially important example of recursive computation that has nothing to do with computer science, I suppose, is simply modeling motion. So if I am located at 1, for example, and my speed is, say, so I'm located, let's start at 0, that doesn't really matter, and then I progress at a speed of, say, 1 mile per hour, then I don't need the explicit formula. I will be just computing. I will be adding 1 at a time. Okay, so so that's the simplest way, the simplest kind of a formula. It won't have any kind of a convergence pattern like this. Okay, so that's here it is. So every time we simply add 1 at a time. 1, 2, 3, and so on. So there is no explicit formula. Once again, if you look at the formula, every time I'm simply having adding 1 plus 1 to this thing. So an plus 1 is equal to, that's how we usually write it, an plus 1. So that's recursive formula. Recursive formula as opposed to this one, which is explicit formula. So as you can see, it depends on n, just like any function. That's explicit formula or functional formula, or it is recursive formula. Both of them are important, but the last one is certainly very common. I have one example that is, let me see if I can remember what that is. It exhibits sometimes, the recursive formulas especially might exhibit very unpredictable behavior. Where is it? I can't remember what that formula is. Well, let me do one that is simpler to begin with. How about I start with 1, I'll start with 0, and then I will, how about I will cut my distance to 1 in half. Every step will be, remember the paradox of Achilles and the turtle, anyone? Well, the ancient Greeks came up with that paradox, is that Achilles, that demigod, cannot overtake a turtle because if there is any distance between them, then while Achilles covers the half distance between them, the turtle moves on, and then once he covers the distance that is left, half of it, the turtle once again has moved on, okay, and so on, and so at no point you're gonna reach the turtle. Okay, so that's the paradox. Yeah, have you heard of it? Yeah. So Zeno was the philosopher. So so let's try something similar, except without the turtle. Let's just go. You can say it's in a similar fashion. You can say that I will never reach that wall over there because I cover the half a distance and then I cover half a distance again, and half a distance again, and so, well, that process will never end. Okay, so certainly common sense tells you that certainly there is no problem, but let's try do that. So I am at 0, and I will cut the distance half at a time, half the distance at a time. So based on my current position, I will know my next position. So it will be what is it? My previous position. So this one equal to my previous position. Okay, my previous position plus what? Plus the distance from my current position to 1 divided by 2. Okay, so 1 minus my current position, okay, divided by 2. Okay, you see the formula? So once again, the previous position in blue, or current position in blue, plus what is my step? It is my distance to 1 divided by 2. Okay, so that time, every time I will be twice as close to my destination as previously. Okay, so as you can see, from 0 I move on to 0.5. Then I move on to 0.75. Okay, and on and on. Okay, cutting the distance at half every time. And if I have not reached 1, so it might give you an impression that I have reached my destination. But certainly, if we go to and give more decimals, you can see that I know I'm not there yet. If you see at the bottom, after 18 steps, I have not reached my destination. Okay, so and you can see that it is indeed steps. If you look at those blue dots, these are our consecutive locations. Time is horizontal, location is vertical. Okay, and we're moving towards 1, but never actually reach it. Once again, we recognize that there is a looks like an asymptote, and if we go back to the well, actually horizontal is not the time. That's the key to the paradox, is that the horizontal axis is not time. It is just the number of steps. Okay, if you wanna actually do the time and plot how do I introduce time into this situation, I take my speed. I need my speed, and then I look at the distance that I have covered, and I simply divide the distance by the speed, and that will give me the time that have taken me to cover that distance. And then what do? I just add those times and see there will be infinitely many intervals of time. So that's the problem with this paradox, that you have to add up infinitely many terms in order to demonstrate that you're gonna reach that wall, or you are gonna overtake that turtle in your lifetime. Okay, so and there isn't really no paradox there, but it is a big deal, because, well, the Greeks did not know calculus, and we do. So let me do it nonetheless. So this is my location. Once again, this is my location. Let me insert time here as an extra column. Okay, so this will be my time. Okay, so how about I copy this? So I start with 0. Okay, here I will take my formula. Let's see, and I insert it here. What happened? Okay. Copy. Just copy. Okay. Here. What? Shit. Doing it again. Okay. So what I'm copying here is my the distance that I actually cover, and which is the same as our time that it takes. So these are my steps. These are the steps that I take right here. That doesn't look right. Okay. Hold on a second. Okay, so I messed it up slightly. So I need to insert the column is I put it in the wrong place, unfortunately. So let's try it here. So this will be my column of time. So and the time will be, then I'll take my distance. I'll take my distance and I will divide it, and that will give me my time. Okay, so this is finally my step. Okay, the step is 0.5, and then on, I was just doing it again. Okay. Okay, let me start over. Okay, so I'll just for my distance, I'll take this minus that. Okay, that makes it simpler. Okay, finally. Okay, so these are my steps. These are the steps that I make during that pursuit. We're trying to reach some destination in what amounts to infinitely many steps. But as you can see, the steps are getting smaller and smaller. Then the question really becomes, well, what is the question? The question is, how do I know that even if I carried out infinitely many steps, wouldn't it be reasonable to assume that it might take me infinitely long to reach the destination because there are infinitely many steps? Even though they're getting smaller and smaller, how do I know that they won't add up to infinity? Okay, so that is the question that the theory of sequences and series later on will have to address. So just because those little pieces, the steps start to diminish, does not imply of itself that you will end up with a number. You might end up with infinity. So that graph over there might be easily misleading. So it looks like it is flattening, but actually it is very easy to see that under certain circumstances that it is just slowing down. But it actually, the examples that we're going to see later on is that the graph that looks pretty much identical to this, but it looks totally flattening, but it's not. It actually is going up and up and up and goes to infinity. So it is a possibility. And then to distinguish one from the other is a crucial part of that part of the course. But this one works out. You cannot demonstrate, you cannot prove that, however, with you cannot deal with infinity using a computer. Okay, so no demonstration, no picture. No, you can, instead of 20 rows, you can have 100 or 100,000 rows. You will never know whether or not you're gonna get infinity or not. So these are limitations of computers, because they can only do finitely many steps, and with finitely finite accuracy. So we're gonna do it differently, naturally. Okay, so that's just an example of a sequence that we do. I just promise to demonstrate that later, so that this numbers in this column, these time intervals will add up to a number, not infinity. Okay, so we'll see that later in the course. And at this point, we are moving on to well, not moving on. We'll just do more. We got to study sequences in a more focused way, concentrated entirely, almost entirely on limits. So like this. Okay, so now it is going to be about limits of sequences. In a way, limits are more important than sequences. So it is, in a way, we're not studying limits as attributes of sequences. In a way, we're studying limits by means of sequences. If you once again look at any of these pictures, you realize that we imagine the graph over there, okay, and then we can figure out its long-term behavior by means of a sequence, okay. And then it means that there might be nothing interesting about the sequence other than its limit. Okay, so in fact it is pretty much what we will be the idea we're going to follow. It is that the cutting piece of the graph, piece of the of a sequence in the beginning of the sequence, obviously, will not change the limit. Okay, so if this is my sequence, the limit is 0 as n goes to infinity. Okay, then what if I start with 1/3? It's not going to change a thing. I still say that the limit is 0 as n goes to infinity. So it is the tail of the sequence that matters. And it determines the limit. So let me define the limit. The definition is pretty much identical to what you see the limit of a function at infinity. So that's the similarity, and hopefully that will help you to absorb this quick. So suppose we have a sequence an, okay, then a number L is the limit of the sequence. Is the limit of the sequence f for every epsilon greater than 0. There is an n. So that n is the cutting point of our tail. Okay, so if we're progressing as far as necessary in order to get close to epsilon, to L, such that this again. Let's call it such that an minus L is less than epsilon. Okay, so we'll discuss this some more next time.